PreonLab as a meshless CFD code based on SPH methodology, which offers some unique advantages for some really challenging engineering problems in vehicle development. And some of those are really large simulation domains, domains with really complicated geometries, complex geometries, especially geometries that should be moving and that have a transient nature to the simulation itself. So whether that's, windshield wipers moving fluid down the windshield, or vehicles driving through rain or driving through a standing puddle of water, it's important to capture all of the transient things that are all of the things that are happening over time in those types of simulations, in order to be able to really virtualize what's going on in the real world. So what we see and what engineers need from CFD, what development needs from CFD is the ability to handle larger domains, but still capture small scale effects, and to be able to do this in more of an as-built condition, or closer to geometric reality, if you will. And PreonLab supports all of those things, with the implicit solver. PreonLab is based on implicit incompressible SPH. With the implicit solver, it means that we can handle really, really large domains. I have users who are looking at, these vehicle water weighting types of cases and handling hundreds of millions or billion particles. Having that many elements in a simulation is huge. And they're doing it on, not a single engineering workstation, but on, traditional CPU-based HPC environments, which is, a huge step for performance. Being able to actually do those kinds of simulations at that scale and turn it around in a time which is actually usable for design teams to make development decisions on is I think what, that's the PreonLab promise, which has been really, really fun to see how we can stretch that and how we can push those boundaries. Because the purpose of it should always be, how can we deliver actionable insights in a virtual environment which matches reality as much as closely as we can. And I think we're doing it, so we see a lot of really cool applications for PreonLab, and usually we focus on these types of free surface problems, and what that breaks down to in the vehicle environment is, are we working with water, or are we working with some kind of oil? And if we're working with water, this is the flagship application really of PreonLab. One of the biggest things that we can look into is, what we call vehicle water management. And one of those tasks is water weighting. So you have, exactly the thing that their teacher in driver's ed told you not to do, which is take your vehicle and drive it through a puddle, which is a foot deep, see what happens, which you should absolutely not do. I don't want to condone that anybody does this in reality, but it happens all the time. There's hours and hours of content on YouTube for people who are making less than wise decisions or urgent decisions to drive through things that maybe they shouldn't. But what can happen there is, if you're coming at speed, the vehicle then, kind of hits the surface of the water. It doesn't disperse very quickly. And there's a lot of forces that happen on all of those underbody components and underbody fascia. So, there's damage that can occur to liners or to fascia based on that first impact. And then once you're in the water, of course, in traditional IC engines, you want to make sure that you're not aspirating that water, that you're not going to breathe that water in. But also there's, quenchant effects, getting a lot of cold water onto hot components, and that thermal cycling that you would like to know a little bit about. And as we move into electrified vehicles as well, there's electrical waterproofing considerations that need to be taken into effect. And being able to design for those conditions way before you have a vehicle prototype is something that we really focus on quite a bit. And with PreonLab, we're able to do those water weighting simulations as early as you have vehicle geometry in CAD, and it doesn't even have to be perfect geometry, but if you know where things are going to sit under body, then we can push that through some water and see what happens, whether that's being splashed up or if it's being completely immersed, and have an understanding on a transient basis. So in the first part where you're entering, this puddle, and then there's a part in the middle where you're fully immersed, you're just kind of pushing through, and then there's an exit portion. And understanding how water is moving around those components at every individual time, which when we compare it to actual tests, there's proving grounds everywhere. They have these waiting channels, and you drive your truck through at 40 miles an hour and you create a big rooster tail. And what you can do is you can put cameras under the hood, or you can do some kind of salt wash. So anywhere that water is, you can wash off a surface, and that way you can look at like the total averaged, or the total result, but you don't know when that failure or when that wetting might have occurred. And that's the value of simulation, is not only can you replicate these test environments in a virtual way, virtualize these tests, but you also get additional insight from simulation in the way that you can slice the geometry at any point. You can look at any tiny detail at any time, but you can also look at, those individual times and understand when the critical event happened, if there was one. And when we talk about PreonLab, that's one of the things that I think we're really proud of. Coming back to that idea of democratizing CFD, which has been this experiment in the industry for quite some time, but the usability of PreonLab is such that people who are not quote unquote CFD engineers, or not people who have spent so much time doing this, but they have that experience on the testing side, are able to use PreonLab to virtualize some of those tests. So we have quite a few users who have that background in testing, but not necessarily in simulation, who have successfully virtualized their tests in PreonLab and been able to extract the same results, which accelerates their real testing, I should say their physical testing protocol dramatically, which is really, it's a huge value, a huge benefit. When we talk about vehicle though, so we can replicate some of these tests that are traditionally done on proving grounds or in rain booths, for example. But we can also do some things that are dangerous to do, or that we wouldn't otherwise really, or that require really a lot of expertise to test. So figuring out, different vehicle paths as it's splashing through water, and testing in environments that, typically the weather presents a risk. That's something that we can virtualize and test some of those edge cases, which is pretty cool. Another task that we also look like is rainwater management. So how water will flow over the body of the vehicle. So if you have rain coming in, do you have some kind of splashing that's happening? How well are the windshield wipers working? And if they're pushing water under the hood, under the cowl, then, where is that going? Is that water managed under hood? Is it not? Is there some kind of splash up from the road that needs to be, accommodated? And this is especially relevant as we're talking about autonomous vehicles. They have a certain set of sensors, which, depending on the technology behind, may or may not be sensitive to weather conditions. So whether that is rain, soiling, or mud splashing up, or even snow, we're able to simulate quite a few different materials and understand how those materials are interacting again, in a transient way. So whether that's splash up or snow actually accumulating in the wheel arch liner, and interfering with the jobs of some of those sensors that are all oriented or are all positioned there around the wheel itself. So we see a lot of really cool experiments, I should say. We see a lot of really cool tests that are being done on the vehicle side, especially when it's related to vehicle water management, whether that's wading, rainwater, snow or mud types of soiling events, and we have, I think, some examples of that, and I'll provide some links. But we can also look at other fluids, and another really strong use case for PreonLab is looking at transmission lubrication types of studies. And here, the complexity of the rotating elements or of the gears has been a huge challenge for CFD, for traditional CFD, in order to bring that in and to mesh it appropriately, and then also to get the motion. And PreonLab as a particle-based code doesn't struggle as much with the geometric complexity. If we have the appropriate resolution of different particles, then we can sample any geometry that we'd like. And it also allows the ability to look at longer timescales. So one of the really strong advantages of PreonLab here is being able to look at transient events such as vehicle maneuvers and how that affects how oil is sloshing around inside these cases, inside the transmissions, right? So if we look at, I don't know, an EV reduction gearbox, for example, typically it's a closed volume, it's a 2-stage reduction gearbox, and you need to understand that at all of the speeds that the motor is going, where the oil will be splashing to inside the case. A lot of times it happens just the same as an IC engine. You put a few quarts of oil in there, but when the engine is running, most of that oil is not in the oil pan where you first put it, right? It goes other places, and the same thing happens in transmissions. And understanding where that oil is going, but also the effectiveness of different oil control devices, whether that's guides or ribs on the housings or some kind of drilling, which should be providing lubrication to bearings, understanding the effectiveness of those design features is important. And even in a steady state way, can be difficult to test as well. So once you get to a certain rotational speed, the oil splashes around, and even if you have kind of a clear case or transparent housing, it can be really difficult to have an understanding of where that oil is going. So again, it's a case for how to couple simulation and physical testing in a way that provides both confidence in your results, right? But also additional insight that you can get from simulation. But in addition to those steady state points for understanding the distribution of lubrication, we can also add in those longer timescales and start to understand what happens, for example, when you're entering the highway on some cloverleaf, right? So you have some lateral acceleration, which is pushing fluid to one side or to the other. Is that long enough that it's going to create an issue? My husband's car, when we get on I-25 in some situations on one particular exit, every time we do that, the windshield wiper fluid light comes on for just a few seconds because the fluid has sloshed away from the sensor face for a point that it sends a signal. Then we get onto the interstate and it all levels out again and everything's good to go. So, and the same thing is happening inside the transmission. So especially in systems where there is an active lubrication device or some kind of oil spray or an oil jet, which comes again also with a pickup, a pump pickup, some oil pump pickup. is that lateral acceleration over that however many seconds, 20 seconds it takes to merge onto the interstate long enough that you're going to be starving a pump? And if so, is that going to create an issue? Which is, I think, something historically you had to wait till you had a vehicle prototype and then take it around and test that out. Whereas now we can do that with, in a virtual environment.